Excellent. So we're live. Right. Good morning. We are now live up here, and we are now live, and I checked the broadcast, and I do this thing does actually pick up my voice, but I may have to spend a little more time here in front, so just so that it picks it up clearly. Right. So the website is not up yet, but I just want to show you that you can watch these videos on YouTube. If you go to YouTube and you search for this, you should get the channel for this course. So there's a little test video at the bottom. And this is Monday's lecture, and this is actually today's lecture. It's being streamed live with a bit of a lag. So in case you need to do that. I'm sure there are tons of admin that you want to sort out. Please ask me afterwards. But for now, I'm just going to press on. Someone just started watching the live stream in class. So I'm just going to press on, and this stuff is not critically important for this year. But having said that, it is also important to know this. If you're a computer science student and you speak to other teachers, lecturers, or students, they're probably going to think you're a bit of an idiot if you don't know this basic stuff. And I know that students only hear 10% of what I tell them, and I only remember 10% of that. But I'm still going to try. Let's see if any of us sticks. So this is about the theory of computation. This first year is all about learning to program, but computer science is not only programming. It's not only about coding. It's also about some underlying mathematics behind the coding. And software is really, really complex. Big software like Windows can have 40 million lines of code. I think, if I remember correctly, Windows 98 had 40 million. How do you write so many lines of code? You have to have lots of people, they have to work together. You can't just write the code. Bill Gates didn't sit down one day and start writing Windows, starting at line 1. You have to develop the code in some kind of systematic way. For that, you need mathematics and some kind of organization. So there is a theory, a lot of theory behind all of this, and we should see if we can get to grips with some of it. So basically, when we talk about the theory of computation, there are two questions we want to ask. What can a computer do? Can a computer do every single thing? Given any program, given any problem, can I write a computer program to solve that problem? And there are some problems that we can't solve. In fact, they're trivial to express, and there are tons of them. So I'm not even going to start. It's too much fun. I need to keep going. If I digress, please stop me. And what can a computer do with limited resources? So how fast will the computer solve this problem if it only has a certain amount of memory? Or if it can go this fast, or I want the problem solved this fast, let's say I've got a big problem to no problems, don't worry about it. I don't know. If I want to solve a certain problem, like let's say do university's payroll, which is really important, forbidden block, nobody's allowed to sit in the forbidden block. It's forbidden because very bad things happen to people who sit in it. They're cursed for 7 years. And we've had bad experiences. Don't sit there. Oh, the whole block is forbidden, yes. That's why it's called the forbidden block, not the forbidden row. It's very important. Right, so if I want to write a program for the university's payrolling, and I wanted to execute at a certain speed, it has to process my salary within 1 day. How much memory will it need? So we ask that kind of question. And what's the trade-off? If I want to go twice as fast, how much memory do I need to buy extra? Speaking of memory and computer speed, tomorrow we'll have a tutorial that'll introduce you to the command line, the environment we'll be using for the first half of the course. And we'll also talk about what kind of computer should you buy. Perhaps you already have some kind of portable mobile device that you use in class to watch lectures, or that they record it. But if you haven't yet bought a PC or a laptop or a tablet, what have you, we'll talk about that tomorrow. And if you have, it's good advice for the future. Right. So when we talk about the theory of computation, we're not talking about specific computers. We don't talk about PC with a 2 gigahertz processor and so much memory, because we want to generalize. In a couple of years' time, the computer will be faster, it'll have much more memory, it won't run the same operating system. So we need to generalize to all possible computers that could exist. And we can do that, and we can talk about those in the theory, using the theory. Right, so the way we do that is to use abstract machines, to say, okay, this is a computer, it's quite complex, it's not really complex. You can buy all the components yourself and build one. It's not difficult, and it's a nice exercise to do. But it seems complex. But we can throw some of it away. I mean, when we talk about the theory, we don't need to think about the keyboard, or even the screen, or even the hard drive. We can just think about a computer having some memory, and the problem is stored in the memory when it starts up, and it'll write the answer to the memory when it finishes up. And we can make many more abstractions. We can make it even much simpler than that. So where does all this theory come from? Well, these people, some of them at least, did all the mathematical groundwork in the early 30s, it says. Not all of them, really. I mean, David Hilbert was really a mathematician, and he did work long before the 1930s. I think by the 1930s he may have been retired or dead. Or alive. Okay. Kurt Gödel was a crazy mathematician or magician. He eventually starved himself to death. His wife went to the hospital, and he was afraid of eating bad food, so he just didn't eat it all, and he died of starvation. But crazy brilliant. I mean, he did some amazing stuff, but not really computer science stuff either, so we just skip him. This guy, Alonzo Church, I don't know much about. He's an American, and he did interesting stuff, but also as a logician and a mathematician, and not really as a computer scientist. Jonathan Newman was an engineer, and he was absolutely brilliant, a really amazing genius. And he did a lot of engineering kind of stuff, but the real computer scientist in this little group is Alan Turing. You've heard of Alan Turing? You know all about Alan Turing, don't you? Because you've seen the movie. You've seen the movie? Only one person. Oh, no, many people. What's your name?
Erica.
What?
Erica.
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 Are you Erica? Okay, Erica. Did you like it?
Yeah.
Was it good?
I thought so.
Good. Right. It's called Imitation Game. It's a new movie about Alan Turing. And I guess I haven't seen it. I don't know what it's about, but I guess it focuses on his work during the war, cracking the Germans' ciphers, let's call it that, Enigma machine. And this guy's in it. I don't know what his name is. Who cares? Okay. And in the movie, they actually show the machine that Alan Turing made. It was called the bomb. Although I think in the movie it's called Christopher or something. It's really called the bomb. And it's really this big, this size, and it was basically almost one of the very first computers built, real computers built. But Alan Turing, even though he did this amazing work, helped win the war, was really important in the war, the Second World War, that is, in case you wondered. His important contribution to computer science is really the theory papers he wrote. He thought of this very abstract way of talking about computers that we are still using. He described a lot of the things that we are still doing that you'll learn to do when you program. And he thought at all the levels, from very low level and doing things like this, building real machines, to the very high level. He was basically the first guy to ask things like, can computers think? How do they play chess? How do we know if a computer is intelligent? All that stuff he wrote about in the 30s. Yes. Right. Why do we want to learn this theory? We want to understand how computers work. We want to understand what is computing and what can we do with a computer. When should I tell my boss I can write this program by tomorrow morning? Or when should I tell the boss, look, the problem you just asked me to implement, it's pretty much impossible, and even if we implemented it in a week's time, it'll still run for a year before you have your answer. So, I mean, that's the kind of thing you want to know. What approach should you use? You can take one problem, give it to two people. One can write a program that works really well, a few seconds. But if you take a different approach, that same problem can take years and years. I should have said that the other way around for dramatic effect. One person can implement a program that runs for years and years, and if you just do a little optimization, it doesn't even need to be big, it'll run in seconds. So we want to know what approach to use for what kind of problem. Is the interpreter gone? She did. I just want to check. Just want to give her permission to go. She hasn't literally. Right. Theory, pure science, blah, blah, blah. Okay, right. How can theory help us in practice? All this stuff is based on theory. We are going to use a compiler, a programming language. That we need a compiler, different kind of program. That's almost purely based on theory. This is an amazing piece of theory that developed that went from something theoretical to something practical really quickly. And we know how to write compilers perfectly. Lots of programs we don't know how to write. We don't know how to write operating systems. Windows crashes all the time. Even Mac OS X crashes all the time. Linux doesn't crash as much, but all these operating systems have issues, bugs. There are many, many bugs in all the software we write, and we don't really know how to write that kind of software. So it's amazing that we do know how to write compilers. They work almost perfectly, and you figure it out. Cryptography. I mean, that's a really important pieces of software that allows us to do banking and transactions. I paid my TV license this morning online. I couldn't do that if I didn't have secure encryption. So cryptography is critically important. Data compression, blah, blah, blah. There are all these different applications, and we have theory behind all of them that we use to do stuff. I just want to make a point. I look at the slides a lot. It's not because I don't know what's on there. It's just that what I see is this. So it's almost impossible for me to read what it says. So that's why I know it's irritating, but I look at the screen at all. Now I can't go back. Oh, there we go. I'll fix this for tomorrow. Right, so let's do a little theory. We're going to start with something called regular expressions. You are going to use them. They're extremely useful. You may not use them much this year, but next year or next semester already, you'll want to know about regular expressions. So the idea is that if we want to describe some kind of pattern, let's say we have a protein like this, and we know that proteins are described by sequences of amino acids. That's not strictly true. DNA is the sequence of acids, and those acids are like instructions for the cells in the body to build proteins. And proteins themselves do contain amino acids, but not as much. So in fact, this picture is of a protein, of a little piece of DNA actually involved in building this protein, this blue thing, or green thing. And proteins is how your body works. I mean, those are the little cogs inside your body that actually do things. But how do we describe a protein? Genetic research is advancing amazingly, and especially because we have powerful computers that allow us to analyze the DNA sequences of organisms. I mean, that, in combination with the ability to sequence DNA, to read the DNA code of organisms. Those two things combined is advancing genetics amazingly. And in your lifetime, you'll probably see an amazing revolution. So it may be, I'm not saying it will be, but it may be that people won't get ill anymore. That we'll just have medicines that are so intelligent that they can just go through your body and eliminate the illnesses. It may be that a lot of people will lose their jobs at the gyms because there may be stuff, substances you can take that will build your muscles for you. You don't have to go to gym. While you sleep, you'll bodybuild in your sleep. What else? It may be that there are substances in your lifetime. I'm pretty sure there'll be substances that cure mental diseases, but also affect your mood in other ways. So things that make you happier, or things that make you feel in love, or things that make you more intelligent. So I think those things are coming. In any case, now I'm digressing, and you're supposed to stop me. Erika, why don't you stop me? Right. So we want to describe all these proteins, and this is a description of what a protein may look like. Not really in real life, I mean, but this is a description of a protein stored in a software. So it's from a system. Just give me a second. So there are many of these databases. They store lots of genetic information, and researchers use them to query if this is an existing protein, or if this is a new kind of protein, or what does this protein do, or where has it been seen, or what's this protein all about. So in these databases, they describe the records. And this is a record of a protein. All these records start with a C, and then there are between 2 and 4 amino acids, which help to form this protein. I thought it's always 3, but never mind. Okay. Between 2 and 4. And then there's another C, and then there are 3 more amino acids. I don't know what they mean. One of the following amino acids, one of those 9, 8 more amino acids, an H, the letter H, and 3 or 5 amino acids, and then an H. So this little string here, C, S, C, G, G, Y, blah, 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 H, A, G, W, H. This is a little description of a protein stored in this database, in one database. It's like a big text file, like a document, a Word document. And now we want to find patterns in this database. It could have millions and billions of proteins, and we are looking for a very specific protein. How do we describe that protein? I mean, if we know the full string, that's also nice and well. But what if we only know a part of this protein? How do we specify the pattern? So that's where regular expressions come in. They allow us, it's basically a pattern language. You can write patterns in this regular language. Here are some applications, but let's go forward and more applications. Let's have a look at this regular expression language. So there are a few operators in the language. One is called concatenation. That's where you just put pieces of the language one behind the other. For example, I can write AAB, AAB. That's really 6 letters that have been concatenated together. That's one regular expression. Each on their own was also a regular expression. And a regular expression like that matches if each of the little parts, individual parts match. So that'll match AAB, AAB, and it won't match anything else. Second operator for regular expressions is a dot, a wildcard. So a dot will match anything. So this little string here is a concatenation of a wildcard, letter U, a wildcard, letter U, a wildcard, letter U, a wildcard. And that'll match things like cumulus, jugulum, I don't know what a jugulum is. It won't match succubus and tumultuous. Why not? Because for succubus, the S will match the first wildcard, which means anything. The U will match the U. The C will match the wildcard. But then the second C in succubus won't match the U, that's the fourth piece of our regular expression of our pattern. So that's a non-match. And if you repeat the same exercise for cumulus, you'll see they all match. Okay, I need to start learning your names. Let's do it systematically. Let's start with what's your name? Daniel. Kinsker. Oh. I'm not going to use my hand. Daniel's in a special case. Daniel wants a succubus. Yes, I just want to know. No, it's fine. I know. A demon of lust. Oh, that's terrible. It's specifically for females, not males. Tumultuous, Daniel. Let's just probe Daniel's knowledge. That's the easier word. Tumultuous, stormy, or mixed up, or chaotic. Cumulus, cloud, juggling. Is it your throat thing? I think you think of jugular. Is it the same thing? Oh. Right, let's move on. Union. Union is an operator for regular expressions. It basically means or. So this regular expression matches AA, the first part, or BAAB, the second part. So it will match AA on its own, that's fine, and BAAB, but anything else won't match. This union is only two parts. You can only match this first part, which is the concatenation of two letters, or the second part, which is the concatenation of four letters. Right, closure, fancy name, it just means repetition, 0 or more times. So A, B star A, the star is a closure operator. It means the previous thing 0 or more times. So this means 0 or more B's. It's a concatenation of A, B star A, and it must contain 0 or more B's. So double A will match. The first A matches the A at the start of the pattern. The B star, B is repeated 0 times. And the last A matches the last A of AA, so that's a match. And the same for this word, which I don't know, Daniel doesn't either. Okay? AB won't match. There's 0 more B's, but there's no final A. And because there's a concatenation of A at the end, we need that A to match. And AB won't match either because there's 0 more B's, that matches. Then there's A, that matches. But then there's a B again, and our little string our pattern doesn't cater for an additional B after that final A. Right, and last thing, we use parentheses, just as in mathematics, to group things together. So when it says here A and then A or B in parentheses, it means that I want to match an A, and then either an A or a B, one of these two, and then at the end, A, B. Not both, but either. Or if I have AB in parentheses star, it means that AB is repeated 0 or more times. And then it's followed by A. So A is a valid string for this pattern. AB, A is valid. AB, AB, A is valid, and so on. That's all regular expressions is, just these few operators, and we obviously can use them to write patterns. So I can use them to write a little pattern to describe this representation of proteins in my database. Obviously, I'll have to have a C, and then it says between 2 and 4 amino acids. So I'm not exactly sure how that is, but it sounds like kind of limited repetition. Then another C, we can concatenate that. 3 more amino acids, it's still tricky. Maybe I have to learn a little more before I can do that. What are these? Surprisingly expressive. Oh, okay. This is good stuff. So, I'll just use my little cursor. Let's have a look at this. Dot star SPB dot star. So anything 0 or more times, any letter 0 or more times, anything at the start, Then I want SPB in the middle of the word, and then I want at the end dot star, so anything 0 or more times. So basically any word that contains S, P, and B. Like raspberry. Daniel, you know that? Checking. Crisp bread. What's crisp bread? Bread that's crispy. Yes, of course. Subspace, subspecies. Oh, boring. Multiple of 3 B's. Wow. Ooh, tricky regular expression. Let's analyze a little. So there's an assumption here that is that I'm only having 3 letters, only A and B. So no other letters in my strings. I could not. I could say anything but a B, but I'm just going to use A. So if I want to describe all strings that contain a multiple of 3 B's, I'm either going to write A star, so 0 more A's, which covers the case of 0 B's, or I'm going to write A star, any number of A's and a B, then any number of A's and a B, any number of A's and a B, any number of A's and a B. That's multiple of 3, and I star that. So this whole pattern can repeat 3 or 4 or 5 times. Tricky, but quite cute if you think about it. I can write stuff like this. So BBB is accepted, that's fine, because it will be one repetition of this star, 0 A's, a B, 0 A's, a B, 0 A's, a B, 0 A's. And one repetition, that matches BBB. For AAA, I'll have to match the first part. It cannot possibly be the second, because even if I have one repetition of this parenthesized expression, that means I have to have at least one B. So I cannot possibly match this side. It must match the A star side. And then I'm too lazy to go through that. And those are patterns that don't match, amazingly. Dot star, anything. You don't care about the prefix, then a 0, and then 4 other characters, anything. And if I search through a list of, let's say, telephone numbers, what have you, I'll find all the ones that end in, where the 5th last digit is a 0. So that one matches because it's not the 5th last, this is 0. But these match because they have a 0 in position all but apart. Fragile X chromosome indicator. I have no idea what that is, but I'm guessing that some people have some kind of genetic mutation. There's nothing wrong with that. You are all mutants. You know that, don't you? We're all mutants of our parents. Every single person is a mutant in some sense. In fact, we are a minority of mutants. We have a strange mutation, all of us, that make us different from the majority of people in the world. Who here has parents that come from Southeast Asia? Don't be shy. Don't you have a Korean? Isn't there a Korean person here? What happened to my Korean student? I only had the one, now lost it. Most people in Asia, in fact, most people in the world, are lactose intolerant. Can't drink milk. And we, because we've been to Europe, come from Europe, are able to drink milk. So that's a genetic mutation that happened pretty recently, last, I don't know, 60,000 years, that may split us off from the rest of the human population. We may become our own species as milk drinkers. But even if they don't know what this is obviously some kind of mutation that influences something, Fragile X. We all have these kinds of mutations in our bodies. Some of them make us less prone to some diseases, but more prone to others, and the other way around for other mutations. I mean, some of the serious ones cause Down syndrome and other genetic defects, abnormalities. But this is the kind of thing that researchers look at when they look at the human genome. It's really tedious to write things like anything except a B. If I want to recognize any letter except a B, I will have to, at the moment, write open parentheses A or C or D or E, up to or Z. Close parentheses. That's really time-consuming, and it's not what I want to do. So there are these shortcuts. Instead of 0 or more, I can write an star for that. I can write a plus, which means 1 or more. Well, you make it more. Making it slow. I'm sorry, I'm really sensitive to low noises. Okay, right. We can write a plus instead of a star, which means 1 or more instead of 0 or more. We could do the same thing with star. We could, if we want to write 1 or more x, we could write x concatenate x star. So that'll give me 1x and then 0 or more additional x's. But for brevity, I can just write a plus sign, which means 1 or more. I do not have to write out A or B or C or D or E or F or Z. I can just write in close brackets A to Z. So the second set of closed square brackets, A to Z means A or B or C or up to Z. And you can write more than one range inside the closed brackets. So you could write A to Z, big A to Z, or small a to Z. You can write both of those, and it'll know that it's all the capital letters and all the lowercase letters. I just said it will know, and I guess you assumed that I meant the computer. But the computer does not understand regular expressions. So these regular expressions are all for specific programs that we use. And there's a convention that they all use the same language, all regular expression language. So most programs understand when you write big A to Z, small a to Z. But not all, they all have their little quirks. So you have to be a little careful. Then, to make it even more convenient, we can write things like 2 or 3 or 4 repetitions of a certain pattern. But it's cumbersome to write that out. So we can often just write braces with a number inside, 5, which means exactly 5 repetitions of the last one. It's a little like star, and it's a little like 1, but it's an exact number. And often you can even write a comma. You can write 5, 7, which means 5 to 7 repetitions of the previous thing. So 0 is actually the same as 0, infinity. And 1 is the same as 1, infinity. So what does this pattern do? It says, I want exactly 5 of these characters, 0 to 9. So 5 digits, exactly. Then a minus sign. This is concatenation. It has no special meaning. And then 4 digits, 4 more digits. So it will match this stuff, and it won't match this stuff. I'm guessing this stuff, which matches, or it may be the new zip codes in the States. I'm not sure. Okay, and lastly, well, 2 things. We don't have to write a range inside square brackets. We can actually specify all the individual letters we want. So we can write A, E, I, O, U, which means any of those letters. There's no range, there's no minus sign inside. So any of those letters. Yeah. And then the special thing we can write is that if you put a little sign like this at the start of a square range, of a square bracket inside, it actually means not. Okay, let's learn more names. Daniel.
Danielle. Danielle.
Oh, yeah.
That was confusing. Yes.
What's this little character called? Danielle? Danielle? The little character that I did not name.
Oh, what was that?
Oops.
remember the actual character.
How do you talk about it when you tell your mother to write one? How do you say it? Why don't you write a copy?
Isn't it happy?
No, it's
I know
not.
that's just a concept.
In Afrikaans it is, but in English this is called a carrot, C-A-R-E-T, and I'll be using that word from now on, so we'll carry. I don't think there's any other name for it. Say again? Copy may be more familiar to you, but if you talk to people overseas, most Americans don't understand the copy of the ear. It's like, I don't get it, so I try to stick to the. We can still write words without the vowels. This is 6 separate words, 6 repetitions of these letters, which are A, E, I, O, U, not. So all the other letters of the alphabet, but not A, E, I, O, U. But we can still write words like rhythm. Rhythm is a word. Rhythm is a word. Okay, right, quickly. You guys are falling asleep, as do all students. I do. After 20 minutes of a lecture, your attention will start lagging. So you must try to wake yourself up. Otherwise, some of you are already asleep. So I'm going to show you a little video just to keep you awake. I'm not going to do this every lecture, but I don't want to lose you so early. Let's just have a little looky. I know it's kind of a waste of time, and I'm so behind, but, you know, come on, computer. Okay, I hope it's just going to work. Even if it doesn't, it's still fun. Okay, you can just watch in silence. I'll sing a little song. That's all. And there's some. It's really hot. Go. Come on! It's so exciting. Now, this goes on for a long time. I don't want him to ski the whole mountain, so I'm just going to speed him up a little bit. Oh no, people, that's interesting. Oh, okay, there you go. I'll just speed him up a little bit. Hang on. Oh, ow. I now realize that didn't really wake you up because it had loud music. I'll rectify that in the future, but should be a little more awake or a little more asleep. We have 9 minutes to do everything, and I've done nothing. So I'm going to speed up a little bit. We have these regular expressions. How do we actually implement them? How does the computer know how to recognize words? Well, how to recognize these patterns in the big text file? It uses something called the DFA. DFAs are really important in computer science. We use them all the time. I hear about them every single day, even though my own research is not about them. We do have to do research on the syllabus. So DFA stands for deterministic finite state automaton. And it's basically a very simple kind of machine that reads a tape, an input, like a word or a regular expression pattern, or a sound file, or a video file, some input stream that's been encoded as ones and zeros. And we'll talk about how that happens on Friday. This machine reads it. I guess you press the start button, and after a while it reads the whole tape, and then it stops. And it either says, yes, I'll accept this input, or no, I won't accept it. That's all it does. It's just an acceptor of inputs. So, for example, I may encode my regular expression on this tape and give the whole text file after that on the tape, or I just want to see. And I will process it and tell me, yes, this pattern matches some part of the text file, or no, it doesn't match. I mean, this is really simple, and you wouldn't think you can actually do anything with this, but this is the basics that our computers are built with. This is how all our computers operate. They're just collections of little DFAs that work together and say yes or no. That's all they do really inside. Of course, there are many of them, and they collaborate in complex ways, but that's all it is. So this is an example of how a DFA works, and oh, I'm going to be so behind. I'm going to skip a little illustration, and I just want to go forward a little bit. In fact, I'll go forward to the end. These regular expressions, are there patterns that we can't match with a regular expression? Are there things we can't express with a regular expression? There are many things. Just like there are some problems that a computer can't solve, there are many things that a regular expression can't match. So it can't match strings with an equal number of zeros and ones, or A's and B's. It can't detect that. There are ways of detecting it, and they use other kinds of machines that are a little more advanced. But DFAs on their own, regular expressions, you can't write a regular expression to match that. A DFA is exactly as powerful as a regular expression. And a regular expression can do anything a DFA can. So in some sense, they're the same thing. One is just a machine, and one is a language. But they really talk about the same thing. Decimal strings that represent prime numbers. You can't write a regular expression, no matter how complex, that describe only the prime numbers. If we could, we'd be rich. Okay, DNA strings, never mind that. Is there something more powerful than DFAs and regular expressions? Yes, there is. This guy is called Noam Chomsky. He's an American linguist and kind of political, radical guy. He's always making trouble. And for some weird reason, he did some early work on different kinds of machines, different kinds of languages. And he invented this hierarchy, which is called the Chomsky hierarchy. We've just seen regular expressions in DFAs, and that's called the type 3 language. But then there are others. There's a type 2, which is slightly more powerful, and type 1, which is even more powerful. And the most powerful is type 0. And for that, the machine equivalent of that kind of language is called the Turing machine, named after Alan Turing, the guy who starred who the movie is about. And we'll definitely look at Turing machines in the future at some point, in fact, towards the end of this course. But Turing machines are the most powerful machines that can exist. There is absolutely nothing more powerful than a Turing machine. A Turing machine can compute anything that we can compute. I told you there are some problems that computers can't solve, and those are limitations because of Turing machines. Those are problems that Turing machines can't solve. So, our most powerful computers are Turing machines, abstractly. If you think about the computer you have on your desk or your laptop, this computer, this laptop, your tablet, your phone even, they all contain computers. But those computers aren't even as powerful as Turing machines. The computers we use are in fact all as powerful as DFAs. We don't use anything more powerful than a DFA. Your computer is just a really, really powerful DFA, but nothing more. And I don't believe that anybody, I know that nobody can build a Turing machine. It's too much. I think that's actually the last slide. Pattern matching. Oh, what do we use these things for? We use regular expressions for pattern matching. If we want to use compilers, like Java, the Java compiler, the one we'll be using to write the programs, we actually need a more powerful language. And I said that our machines are all DFAs, so how can we use a context-free language for our programs? But there are small ways that even a DFA can sneak around and become a PDA for a short time. And the same for LBA and Turing machines. A DFA can pretend to be a Turing machine for a very short time. And that's how our computers actually work. Okay, those are the slides. I'm going to stop now, and I'll see you again tomorrow at 2 o'clock in Narcha, and Narcha GNH. Yes, I got that. Shh, shh. This is very important. The website is not online. I'm really sorry about that. But it's open tomorrow. Okay. Narcha GNH.